Okay. I apologize in advance because I'm going to take slides from an hour talk and condense them to a half hour by skipping through and jumping some slides. So I didn't prepare a special talk. Oops. So really there will only be two parts to this lecture. The first part is exactly what Carrie Emanuel and I were talking about. Namely, you can add stochastic variability to a model. When is that just noise, an irrelevant noise, or when can you add stochastic variability to reproduce intermittent coherent structures in nature? So I'll be talking about that in a idealized environment in the first 15 minutes of my talk. And I'll provide a context where I show you how important that is. And then secondly, I'll be talking about how to take models that are imperfect. And boy, our climate models are for the world's hardest engineering problems, and they're highly imperfect. And how can you systematically train them to improve their long-range forecasting capabilities? So that's another topic, actually, that, let's see, is this jumping? Yes, okay. So what I'll talk about in my first part of my lecture is how to use a stochastic multi-cloud model to improve tropical convective parameterization and give you a paradigm example. It's a paper that's going to appear in the Journal of Atmospheric Science. These slides are a little old. So current operational general circulation models have several 800-pound gorillas that all the experts know are not well represented. Amongst them are tropical variability of clouds, etc. The tropical variability of clouds should not be taken lightly. Almost all of our long-range forecasting skill for the mid-latitudes sits on understanding what happens in the tropics 2 or 3 weeks earlier. It's not an accident that there are 16 major field campaigns going on in the world devoted to understanding what's happening to clouds in the tropics. Okay. And unfortunately, the general circulation model, convective parameterizations, often fail to capture the highly intermittent organized structures. There are other alternative approaches, and I'm one of the people who's been working on them, called superparameterization and cloud resolving modeling, but they're still too computationally expensive to have any chance of applying to long-range climate forecast problems. So stochastic convective parameterization is a computationally inexpensive way if it can succeed in assessing the missing variability in the tropics. So let me show you the observational record, and my apologies to my friends at the Geophysical Fluid Dynamics Laboratory, who amongst the 18 Intergovernmental Panel for Climate Change models have one of the best mid-latitude climate models. So the observational record processed from satellites gives, so here is frequency, here is zonal wave number. There are 40,000 kilometers, so 40 wave numbers along an equatorial circumference. And this is the intraseasonal variability in the tropics, 30 days. There's a very famous wave that's very important for long-range forecasting. Essentially, none of the models even now get this wave at all or any of its characteristic structure. This is the Madden-Julian oscillation, a low-frequency wave of extreme importance for seasonal forecasting and monthly long-range forecasting for the mid-latitudes, the subtropics, and the tropics. It influences cyclogenesis and long-range weather, for example, even in Europe through global teleconnections. Here are the weather waves of the tropics, convectively coupled Kelvin waves and 2-day waves. And you can ask how a typical general circulation model with its 150-kilometer meshes does for this tropical variability, and you can see that none of it. And this is one of the 800-pound gorillas that people don't like to tell you about climate change problems and the uncertainty with water and water vapor prediction. So what I want to describe is a sequence of reasoning of how to trick bad models to behave better. by using a stochastic multi-cloud model, which we introduced a year ago. And this stochastic parameterization is based on a Markov chain lattice model, where each lattice site is either occupied by a cloud of a certain type, congestive, steep, or stratiform, as we'll see, or as a clear sky site. The convective elements will interact with the large-scale environment and with each other through convectively available potential energy, which is standard, but also importantly, middle troposphere dryness. In the simplest setup of the model, we're taking the Occam's razor strategy. We'll let the interactions on coarse meshes be generated by the model itself, and we will solve individual columns through a very computationally expensive Gillespie algorithm, which will count the number of cloud types and how they interact. Okay, so I'm going to study this in an idealized framework and show you how you can develop a simple model which you can trick to respond to nature. So what happens is, here's a typical event in nature. So I showed you convectively coupled Kelvin waves. Those go on scales of about 1,500 kilometers. There are squall lines in severe weather systems which evolve on scales of 150, 200 kilometers. And then there's the Madden-Julian oscillation, which really is a planetary scale envelope of all this activity, evolving on 20,000 kilometer regimes. All of them have this characteristic structure. So most of the time, convection is just clouds rising, nothing. Under the right conditions, though, they trigger spontaneous organizations I've just gone through by inducing upscale transports with shear. And the prototype of what happens is, first of all three of those structures statistically have cumulus congestus clouds in front, which heat the lower troposphere and have radiative cooling above them, have deep anvil clouds, which are the deep penetrative convection, and then create, through condensational heating from the water phase, these are condensationally heating driven clouds, and these are the deep penetrative gusts. The general circulation models roughly only have a surrogate of these. Some of them are now starting to put these in, and essentially none of them have unresolved versions on their coarse meshes of these clouds. And these clouds are the stratiform clouds, so they have radiative instability associated with them and condensational heating from water phase to ice phase. They also have cooling below, which is created by evaporation of stratiform rain and induces downdrafts over a boundary layer. So what we'd like to do is develop a parameterization that will spontaneously produce the right variability with that kind of coherent structure, not just random noise. So that's the key thing. So the multi-cloud model is a simple paradigm model, and it has, exactly as I showed you on the previous slide, shallow water equations with heating associated to the three cloud types. So there's a deep heating mode. You don't need to know the details, associated with the deep penetrative clouds, and there are congestus and stratiform clouds associated with the second baroclinic mode. The first mode of the troposphere has this kind of bow-shaped heating. The second mode has this wiggly heating. So you either cool from below and heat from above, or vice versa, for either congestus or stratiform. And there are simple dynamics for it. Now I have to tell you that putting this multi-cloud model into NCAR's next generation dry dynamical core automatically already produces, in an idealized setting, a pretty good Madden-Julian oscillation, which is something that was absent in general. But now I'm going to play the game of a stochastic lattice model. So what we're going to do is take our big grid box and simply have a function that counts the number of clear sky sites, the number of congestus clouds, the number of deep penetrative clouds, and the number of stratiform clouds. And it's going to be 30 squared in all the numerical experiments I'll show you. And what we're going to do is have interactive transition rates for how those clouds are created. And they're going to be motivated by a following fact. Many of the general circulation models use what's called an Arakawa-Schubert parameterization, for example, and it's based on convectively available potential energy. What that means is if a parcel is ready to convect, it should rise very quickly and make a deep cloud. Well, that's not what really happens in nature. What really happens in nature is you create congestus clouds first because of entrainment of dry air as a parcel tries to rise. So what you should have is you should have the low-level convectively available potential energy playing a role for creating congestus clouds, the overall convective available potential energy, and the dryness of the troposphere. So the transition rates amongst the cloud types are defined in a very simple way using those. So formation of congestus clouds can happen when there's low-level convectively available and the upper troposphere is dry. That's a typical example. We don't allow, for example, formation of stratiform clouds directly from clear sky. So there are a bunch of very plausible physically motivated interaction rules with which we will just run here. So now we'll take a time series of what the stochastic model will do just in a column with no interaction. And what you should focus on in this busy slide, and I hope it comes out, is you see the three cloud types are in beautiful phasing. So as we increase time here, the green ones are congestus, the solid lines are deep, and these shaded lines here are stratiform. And what you see is spontaneously a lot of the events are harmless and don't do much. But occasionally they'll build a big intense burst, followed by another big intense burst, followed by another big intense burst, followed by not much happening. That's really what nature is doing. So we're building a noise model to mimic nature, not a random noise model. So this is what I've just shown you blown up. So now I'll take a standard test model. So a standard test model is a Walker circulation. So the Walker circulation, for people who aren't atmospheric scientists, is the simple circulation of rising air along the equator. I'm just going to do an east-west model with no north-south variation. So it's got an x variable of 40,000 kilometers and a vertical variable z. So what we'll have is a warm pool where we do heating, like over the Indonesian marine continent, the Western Pacific, and the Eastern Indian Ocean, where air rises and then it sinks in the mean. Of course, there's really tremendous variability about that mean. So that's a standard test model. And what I'm going to do is run the multi-cloud model in a bad regime, first of all, deterministically, where it has a plausible Walker circulation and variability, but the wrong variability, just like a typical general circulation model has if it has any variability at all. Here's an example. And so you get very regular waves, convectively coupled waves with not the correct vertical structure moving over a Walker solution. So if you look at these waves, they don't have this characteristic tilt that I talked about, and I don't expect the non-experts to follow this part. And now let's look at the Walker circulation when we just take the same parameters in the model and trick the model stochastically with this variability, mimicking what we know is happening observationally in nature without a lot of tuning. First of all, you see tremendous variability of congestus over the warm pool where we're heating the most, deep, and stratiform, as here. And when you see the fluctuations, you see something that looks much more like nature. Let me show you the moisture. And so what you see is the low-level humidity is, first of all, bubbling up and down, but with intermittent coherent waves being ejected from time to time from this warm pool. So that's restoring variability like nature, as I'll show you in the next slide. So here now is a comparison where we'll look at the precipitation. Here is a cloud resolving model run with phenomenally high resolution, 1 kilometer on a 4,000 kilometer domain. Here's the multi-cloud model stochastically run on a 40,000 kilometer domain. This is unbelievably cheap. Look at the precipitation profiles, and you have to be struck by how much, a very hard quantity to get. The precipitation here looks like the precipitation there in time. The second thing that happens, which is a good feature, is it's known that the convectively coupled waves produce intense intermittent events away from the warm pool, where there's the highest evaporation, and here are signatures of them here. Okay, so the nice message here is also when you look at the structure of one of those intermittent waves, it now looks like that deep congestus stratiform paradigm I've talked about. Right here is the congestus leading the deep, leading the stratiform that I talked about earlier. So you can do statistics, and the very nice thing you can do is you can scale it up. So those were results with a 40-kilometer grid. And if you scale the same results up with a stochastic 160-kilometer grid, you'll see you get almost the same variability and same structure. So what we have is a stochastic multi-cloud model that way outperforms the deterministic counterpart. It's a noise model, but it's a physics-based noise model, combining applied math ideas and physics ideas, and it provides higher variability. And it can be scaled to work on coarse grids. So the idea is actually for the future, in a whole bunch of problems, sea ice modeling is actually another good one if there's going to be any sea ice left in 20 or 30 years to model, for variability, to actually trick your models to respond to the right physical variability by building an intelligent, very cheap parameterization. And this can beat the curse of not being able to handle the model. So now let me skip, and I've kind of summarized that part. And I'm off to part 2. I did start a little late, by the way. So I should be 15 minutes through. I'm 18 minutes through. Okay. Okay, so now I want to talk about quantifying uncertainty using empirical information theory and fluctuation dissipation. And I just want to give you a taste of what this work is. It's exactly in the same spirit. It's how to use noise to improve models and improve long-range forecasting. So there's a series of papers which you can see in the Proceedings of the National Academy and earlier on exactly this problem. So everyone knows the practical questions for climate change. So what we'd like to know, and what we very much like to do, is how to measure the skill of a given model in reproducing the present climate and predicting the future climate, and how to make the best possible estimate of climate sensitivity that changes in external and internal parameters by using the imperfect knowledge available. The difficulty, of course, with climate change is we don't really know the dynamics for the actual climate. We just know that the equations of fluid dynamics are valid on large scales, and we know a number of processes, but we don't know the model generating climate. So empirical information theory is a good way to use this, to assess these ideas. And I'd like to advertise that there's a real role for going in between statistics, applied math, and physics-based models. And that's really what all of this work is geared toward, going amongst and all those 3 different techniques. But typically there are some functionals for the present climate that we measure, like the temperature in the northern hemisphere, the temperature over North America, the temperature over the globe, etc. And what we should do is, based on those measurements, we have only one climate consistent with those measurements. It's based on the information we have. And empirical information theory picks the least biased probability measure associated with those measurements we have of the climate. Given those measurements, then, we'd like to get the, given an imperfect model's probability density, in our measured climate density, what we'd like to do is measure the lack of information in our probability density predicted from perhaps an imperfect model compared to what we know about our perfect model. And there's a unique way to do this, which is the relative entropy. If you could take infinitely many samples, asymptotic limit, of course, this comes up in large deviation theory, but that's very far from the regimes I'll be applying this for. So this is not a metric, but it measures the lack of information in a probability density Q compared to P. It's non-negative with equality if and only if P is equal to Q, and it's invariant under general nonlinear changes of variables. Well, if we made L measurements of the present climate, our perfect climate we can call a probability measure, which we don't know, but a simple application of this idea is the relative entropy P of pi L it precisely quantifies the intrinsic error compared to the present climate of the L measurements we've made of our given climate. So what we want to do in an atmosphere-ocean model is take, in a Platonic ideal world, measure this intrinsic model error. Take the true climate and see how well our model will do. And I don't mean just for climate, I mean for climate change, climate perturbations, long-range forecasting, and that's everything. I'll just give you a taste, though. So here's how you should objectively think about improving models. If you have coarse-grained variables you want to understand, the best model in your class should be the one that has the least additional, the smallest lack of uncertainty compared to the perfect model. And if you actually improve your climate models, either through higher resolution or improved parameterization, what should happen is actually this number should go down. So improving the mean may not be a way to have a climate model go down in its total information. And that's right now the strategy adopted typically. So here's a nice little mathematical fact that to calculate this unknowable object, you could calculate it as an intrinsic error of taking the L measurements of the present situation you're measuring plus a functional you can calculate, since this only involves the L measurements of the perfect climate you have available and the L measurements of the model. So if you want to do that abstract minimization, you can do it with data right here. So from a practical point of view, I'll be very happy if I get climate scientists thinking about something that those of us in the turbulence community know very well. If you want to change the mean or assess how well you're changing the mean, you better understand how the fluctuations are changing, and they're one and the same, because the fluctuations affect the mean and the mean affects the fluctuations. So for a Gaussian distribution, what we have is this relative entropy, includes an assessment of how well the model does for the means, divided by the covariance of the model. This is the signal. And then the dispersion, which is the information content in a fancy way of the variances. So this is the signal part. This is the dispersion part. So now let me show you a simple example where there's an intrinsic barrier. So my earlier slides pointed out that there can be intrinsic barriers in models, information theoretically. They can't be improved. Here's the world's simplest example of such a model. So our perfect model is going to be a system of two linear stochastic equations, and what we'll only know about is U, and this will be an unresolved variable, which we don't know in the actual climate because we don't know its dynamics. Well, this has a smooth Gaussian invariant measure if the trace of the 2×2 matrix is less than 0 and its determinant is positive. A typical imperfect model would try to just take the variables we have and under-resolve them. So a typical imperfect model here will be a linear scalar stochastic model. Okay, so this is like our climate model. This is like nature. I claim that even in this simple model, there will be a severe information barrier. So you can easily see let's tune the imperfect models as much as we can. So let's match the forcing, and let's match the variance response and the mean response. So they're matched. There should be a minus sign here if this in the model equals this and this equals that. Well, we care not only about matching the mean and the variance, we care about getting the correct response in climate change. So the response can easily be computed for the theoretical model, delta U, and for the perfect model and for the model with model error here. Now notice, you can easily satisfy those two conditions and have A positive. If A is positive in the natural system, our model will give the wrong sign of the response. So what that means is their information theoretically, we asked could we do the climate change problem with this class of models and play around with them and improve their parameters even though they have perfect model fidelity. And what you can compute is the additional information in the true climate compared to the model is this function. So you try to minimize it. Notice when A is positive, you'll minimize by saying gamma m has to go to infinity and gamma m has to stay finite and positive for your model to have a climate. So no minimum exists. On the other hand, to be less than 0 in nature, if you minimize the lack of information, you can have a very imperfect model. It will match the mean, the variance, and predict the climate response, provided you use that information theory principle. The minimum is right here. So let me jump ahead and show you an exactly solvable test model for climate change science. And of course, as an applied mathematician, I want to emphatically endorse what Carrie Emanuel has been saying. Too many people are running very, very complex models, and they don't think about simple models to validate and test what's happening. So a very simple model for tracers, which has the advantage that it takes a mid-latitude circle. So think of the tracer as varying along a mid-latitude circle with a north-south gradient. That's typical. Think of having an east-west zonal jet, which has a mean part and a fluctuating part. And think about having turbulent Rossby waves that transport things meridionally. Then it's very easy to show that this tracer satisfies this simple advection diffusion equation with a mean gradient. And the beauty about this problem is it's statistically exactly solvable. And not only is it exactly solvable, it has regimes, rare events, and intermittency, much like tracers in nature. So David Neelan at UCLA has been documenting that tracers in nature have very strong exponential tails. This model has highly non-Gaussian statistics with strong exponential tails. It's got you can impose an energy spectrum of the turbulent Rossby waves. Here's a typical one looking like a toy model for the atmosphere. And then the tracer spectrum that comes out is one that looks like -1, a famous number for tracer spectra here, and a faster decay for higher wave numbers. So let's look at how much information is contained. People are interested in global forecasting of temperature, regional forecasting. That just means we coarse grain more and more. So how much of the fraction is in the signal part and the lack of information? In other words, tuning the mean. Well, this is as we vary in the season with our trial model. You see, as we require more fine-scale information in our tracer, we should spend more time thinking about how to get the variance of the tracer right. Now let me show you at the final slide in my talk, stochastic parameterization. So most climate models have too little variability and have an eddy diffusivity put in, either explicitly or implicitly. So now we're going to take a bad climate model and see if we can use information theory again in the same spirit to trick that model to perform better by adding stochastic noise forcing. So this is correlated space-time forcing of a certain sort. And for a given parameter of the eddy diffusivity. Depending on the number of modes you have, there's an optimal way to improve your model so that it matches information theoretically, the climate mean and the climate variance in this systematic way. And you see the optimal eddy diffusivity for the noise occurs. Here would be a standard engineering guess for the eddy diffusivity. Here would be none, and it's about 1/10 of it. Now, I won't have time to show you this, but it's in all those papers I referenced. And this is simply not going to be talked about in the lecture. So so let me go back to maybe this last slide. Okay. So I'll just report some results to you here now. So there's a reason linked to the fluctuation dissipation theorem. It has nothing to do with equilibrium statistics, by the way. We can do all kinds of disequilibrium statistics, and we've done them in all kinds of papers. So the real ramp forcing climate change. But it's not obvious here, but as all I want to say is this improved model that's tuned for the climate automatically has a very good climate response because of this link I told you about testing models well in a training phase using fluctuation dissipation ideas and then guaranteeing their long-range forecasting response. So I just showed you a very simple model where climate sensitivity can't be inferred from tuning a climate model well. There's a barrier information theoretically. And what I believe is there's a real future of mathematical, statistical, stochastic, and physical reasoning for improving some of the hardest problems in climate, atmosphere, ocean science, and improving our ability to do prediction from merging all of these ideas together. So with that, I'll just stop.
Yeah, so maybe I would like to understand a little bit better in what sense you are using the term fluctuation dissipation theorem. So normally,
yes, okay. So I'm using it in a sense. So there are nice published. I have a book from 2005 called Information Theory Stochastics for Complex Systems. You'll see chapter 2 of that book discusses it. It's the fluctuation dissipation theorem for turbulent, stochastic, dynamical systems. There's even a rigorous theorem due to Martin Heirer and myself justifying that theorem under minimal hypotheses. And we're applying it to really turbulent, chaotic dynamical systems in large numbers of degrees of freedom. So what it says is you can compute the response to suitably small-scale forcing, which doesn't have to be stationary or steady or anything, by computing suitable statistics of the present system you're observing. And there's a whole methodology, a whole bunch of algorithms. Grant Brandstatter at NCAR, myself, Raphael Abramoff here in Chicago at University of Illinois, Chicago. There's a whole literature of people involved in applying these things to large dimensional systems. So that's what I mean by fluctuation. I don't mean the identical gas particle statistical physics fluctuation.
have white noise statistic on that thing that at one time people have
No. And that's you're actually raising a really important point. You can make bad models like a linear regression model that have their own fluctuation dissipation theorem, but that doesn't mean that's the fluctuation dissipation theorem of nature or of your complex model. So you're absolutely right.
But didn't follow a lot of what you said, but you're adding these stochastic forcing terms to your model, and that makes a lot of sense to me. So it wasn't clear to me in the future whether you're assuming that the variability of those stochastic terms are going to be different or the same, and if they're going to be different, how you're trying to figure that out.
Okay, so the way I'm trying to figure that out is I didn't tell you in the lecture in any detail. I just wanted to get people thinking. Maybe it's the same idea, so Tim Palmer and I have been kindred spirits for, Kerry mentioned Tim Palmer from ECMWF. He adds a kind of ad hoc noise, so I'm just trying to get people to realize noise does good things, and there should be intelligent understanding of noise sometimes. So for the fluctuation dissipation ideas, here's what you do. In the training phase, so the 50-year historical record where we observe climate. What people should care about is adding the right noise levels and tuning your models, again in a data assimilation context for climate change, to measure not only getting the means well, not only the variances well, which I would be delighted if people start thinking about the variances, but also the time correlations of critical functions. So that's the key thing. So the continuing work says if you do that well in a training phase, you will have long-range forecasting skill with your model. Of course, that's under the assumptions of the fluctuation dissipation theorem, meaning that your time-varying change of the response is not abrupt. Your forcing is not incredibly abrupt, meaning that there are some other, it's within the context of what the hypotheses allow. So a change of a small, all these typical climate change temperatures are well within that kind of ballpark. We have a paper with Grant Brandstatter where we've actually checked that in an atmospheric GCM, for example.
But you're right, there could be hidden uncertainties.
You're right.
Men might do some incredibly crazy
Men
thing.
might do some incredibly crazy thing we don't know about.
To affect climate. And I'm not saying it will work.
Affect climate, and I'm not saying it'll work for that.
But one of the interesting issues in climate sensitivity is the relationship of the equilibrium climate sensitivity after the ocean comes into equilibrium, which is what you see at what Isaac Hull called transient climate response. And even in a linear sense, I wonder whether fluctuations observed on, say, the centennial timescale actually allow you to extrapolate.
So
you probably remembered I had these slides with those coarse grainings. There were some slides on there in that very issue. So a lot of people care about what's the role of initial data versus forcing for decadal, 20-year, 30-year climate change forecasts. So in continued work, well, I might as well just flip. So this is work with my postdoc, Dimitri Giannakis. This is the kind of thing where we're extending the ideas. Exactly. So these are two papers that will appear in Journal of Climate. And it's exactly using information theory exactly in that kind of context combined with the same circle of ideas. How much are coarse grains effects of the initial data and changes in forcing imprinted in the changes in your system? I think this is what you're asking. So,
if you're interested in how much the climate is going to warm after 1,000 years, when the ocean comes into equilibrium, do observations of fluctuations on the time scale of only 100 years give you enough information to address that?
They give you a shot to do that. They give you a rational basis, at least verified in simple models, for how to do that. So that's what I would say. I don't say the problem is solved, but on simple ocean models, it gives you a lot of insight. So not on the real nature of ocean.
But how you define your method is improve the model. The model is how do you define the model? You improve the model. The model can be right on one side, one thing can be wrong on other variable. There's many variables.
Well, that's exactly
what I showed you in the example. I had a two-dimensional stochastic system. My imperfect models were a suite of one-dimensional models. They're highly imperfect for that two-dimensional system for short-range forecasting. Yet, there's a way to use information theory to show two things. If nature has one sign, no matter how much you improve those models, they'll stay bad. And there's a way to take those models, even though they're bad for short-range forecasting, and make them good for long-range forecasting. So you're right. I think when you have bad models, you will always have the deal that some aspects will be improved and some aspects will be ruined. Right now, the climate atmosphere-ocean community takes the models that do the best job for 2- and 3-day numerical weather prediction and works in that end and don't think about what's happening in the other end for models and how to improve models. What we're trying to do in our theory work is think about the other end. And that, of course, is a hot, important topic right now in climate change. What's going to happen in the next 30 years or 20 years?